Today's lesson is lesson 2, definitions from undefined terms, which in lesson 1, we learned that undefined terms were a point, a line, and a plane. So today we're just going to build off of that. Remember, it's a video, so pause it and rewind it as needed. Before we get started, I would pause it right here and kind of create something that looks like this table that I have in here so that once you play the video, you can just kind of copy and fill in the spots that I'm filling in. So the first section, 2.1, goes with your 2.1 workbook, and the new term we're going to learn is segments or line segment. So a line segment, or sometimes we just refer to it as a segment, is a piece of a line. So we're going to get into the notation, but I'm going to go through the example first. So if I have a line and we draw a line with like a straight line with arrows on the side. Remember, a line extends forever in both directions. Even though we can't draw it that way, we represent it with arrows. And a segment is just a piece of that. So I'm going to put a couple points on my line. We'll call this point A. And then point B, and there's this section between A and B. That would be a line segment. So it's just a piece of the overall line or just a portion of it. And the way that we would write that in kind of like shorthand instead of like writing out segment AB is our two capital letters of our points, so A, B, and then with a small line above them. So that means line segment, and it's read as segment A, B. Okay, moving down to the segment addition postulate. I'm just going to read it along. So it says, a segment addition postulate states that if point B lies between points A and C on segment AC, then the distance between A and B plus the distance between B and C is equal to the distance between A and C, which feels like a mouthful. And a lot of times the hard things about the postulates is they feel so wordy, and sometimes, at least for me personally, the words make it seem more confusing than what it's actually trying to say. But it is a skill to try to develop and understand how to kind of translate a postulate or just math rules in general into something that kind of makes sense in your head. So I'm going to go ahead and draw a picture. So I'm going to start with, it says that we have segment AC, so I'm going to draw a segment. So we'll call this point A, and then this point B. And then it says if point B lies between points A and C. So point B is going to go somewhere in between them. Sorry, I was supposed to label this as point C because it was segment AC. So the segment is going to be like kind of in between those 2 points. And then it says that if point B lies between A and C, so B is going to go somewhere in between A and C. It doesn't matter where, just somewhere in between. So we'll call this point B. And then this part says then the distance between A and B, so the distance between A and B, plus the distance between B and C is equal to the distance between A and C, which that's this whole distance. So now that we see the picture, like that totally makes sense where we just, if we take 2 segments and we put them side by side, then their total distance is going to be the sum or the like 2 separate distances added together. Okay, moving down to 2.2. Our 2.2 section is about circles. So I know we know what a circle is, but the more academic definition is all of the points in a plane that are on the same distance or that are the same distance from a center point. So I'm going to skip to example again and then go back to notation. So I have my circle, and every circle has a center. And if we read back through the definition, it says all the points in a plane that are the same distance from the center point. So all of these points around here are the same distance from that center point, and that's what makes a circle. So one thing about a circle is it has a center, and we need to name the center, and it's named with a capital letter. So I'm going to name it center C, and it can be any capital letter. It doesn't have to be C. And then the notation is just kind of like a smaller version of the circle example. So it's a small circle with a little point in the middle for the center. And then right next to it will be the capital letter that the center was named after. And then this is read as circle C. So the notation, the shorthand for a circle is pretty much drawing a small circle. So hopefully that one's a little bit easier to remember. Okay, and then next we're going to find radius, diameter, and arc. But before we do that, I just want to review what each word means. So on the right side of the page, you'll see this helpful definition section. So first we'll review what a radius is. So it's a segment in a circle with one endpoint on the circle, so on the outside of the circle, and the other endpoint at the center. So basically it's a line or a segment that goes halfway across the circle, but it does touch the center point. That's kind of really key. So this circle itself has a few different radii. Radii is the plural, kind of like cactus and cacti. So that word is spelled Radii, and it's the plural of radius. So we're going to find each of the radii. So there's one right here. Goes from the center O to the outside of the circle B, and it's a part of a line. It's a segment, so we're going to use that line segment notation. So we're going to call it segment OB is one of the radius, and we put that line on top to show that it's a segment. And then another one here goes from O to A, so segment OA. And then a third one goes from O to C, so segment OC. And then that's it. There's only three. The radius specifically just have to be just only halfway. So there's one that's halfway right here. It basically is any line or line segment that extends from the center to the edge of the circle. Okay, and then moving on to diameter. So it's the line segment whose endpoints are on the circle, so on the outside of the circle, and the midpoint is at the circle's center. So basically the diameter is a segment that goes all the way across the circle, but it does have to go through the center. So for example, the one that I just drew would not be a diameter because it doesn't cross through the center. So on this circle, this is the only diameter that's given to us, and it's also a segment because it's just part of a line. So we'll call it segment BC, or you could say CB. The order doesn't matter. We can switch that. And then the last one we need to talk about is arc, which that one we don't talk about as common in math classes, so it's okay if you don't remember. So an arc is a segment of the circumference of a circle. So I'm going to draw a little sketch. You can add it into your notes if you want to or not, but it's just to kind of help us understand. So I have a line, right? And then if I kind of pick out a piece of that line, then it's a line segment. An arc is like a segment of the circumference. So instead of being all the way around the circumference, it's just one little portion of it. Or if you think of the circumference as the crust of the pizza, the outside part, an arc would be your slice's crust. So if this is our little slice right here, then an arc would just be our crust that we eat or don't eat, depending on if you're a crust person. So this one has a few different arcs. We're just going to list a couple. So one we can list is BA or AB. And the way that we write arcs is kind of like a line segment, but it's with a curve on top instead of a straight line. And that means arc BA. And here's another one that we can list. So it goes from A to C. So I'm going to call that arc AC. And those are the only two that we're going to list, but they're not the only two. So technically we could list BC, or if you wanted to get really specific, you could include more than two letters. You go arc BAC. There's a bunch of different combinations. The next section is about arc measurements. So starting on the left side or the left box, I'm just going to go ahead and zoom in so there's not so much information on the page. So up at the top, it says a circle has a measure of 360 degrees. So all the way around the circle, we measure at 360. And then an arc measure is the number of degrees out of 360 that are included in the arc. So I'm going to draw a picture just to help us make sense of this. And let's say, picture this is I keep using a pizza reference because we use circles, but let's say this is a pizza and we have to cut it ourselves and we're super hungry, so we're only going to cut it into fourths. Well, all the way around the pizza is a full circle, so it's 360 degrees. But if I wanted to find just the arc measure of my personal piece, well, I'm taking that 360 degrees and I have to divide it by 4, right? Because there's like 4 different, like, of the same size pizzas or slices. So that would end up being 90 degrees. And if you notice, it's also kind of like the same angle that we have inside there. So they do end up matching up. Talk about that more later on. But the way that we would write that is we need to make sure that our arc has points so we can kind of label it. But we would say the measure of arc AB. So measure is like a small m. It should kind of be a little bit more cursive than that, so I'll fix it. So the measure of arc AB is equal to 90 degrees. And then now that we have a picture that goes along with it, I just want to read through the definition once more. So an arc measure is the measure of degrees out of 360. So we took our entire pizza and then our arc was just a portion of that. The portion out of 360 was 90 degrees. So the measure of arc AB is 90 degrees. And then the next section, or not next section, but next part of this section is defining adjacent arcs. And the word adjacent just means like next to each other. So if you want to write that down and then leave a note, that adjacent is just like a fancy word for next to each other. So adjacent arcs means 2 arcs that are next to each other or they have a point in common. So on this picture, AB would be an adjacent arc, and then BE. Those would be arcs that are adjacent to each other. So AB and BE are adjacent. And then we have one more addition postulate. This one's an arc addition postulate, which I'm going to go back up really quick to our segment addition postulate. That's this whole section right here. So pretty much the segment addition postulate felt kind of wordy, but it basically just said if you add 2 individual segments, you'll get their total distance. And that's what the arc addition postulate says. Oh, sorry. That's what the arc addition postulate says as well. This is not in the right notes. I don't know what happened there. Cool. Now we're back. Okay, so the segment addition postulate basically says if you add 2 separate segments together, you combine them, then you get their total distance. So that's what the arc addition postulate says as well, but it's with arcs instead of segments. So right here, we'll read through the words first. It says the measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. And then this math section right here is just saying that the measure of the measure of arc ABE, so ABE, this entire thing, is equal to the measure of arc AB, so just this smaller portion, plus the measure of arc BE, this portion right here. So if we add the 2 separate adjacent arcs together, we'll get the total arcs measurement. Okay, moving down to 2.3, this is the last section of today's notes. 2.3 goes with the 2.3 workbook, and it's all about angles. So the new term is angles or angle, and it is formed by 2 rays with a common starting point. That common starting point is called the vertex. So same thing, I'm going to draw an example, and then I will go back to notation. So a ray is kind of like half of the line, I guess. Technically, they both go on infinitely, but a ray has an endpoint and a line does not. So I'm going to put an endpoint right here and then extend a ray out. And I'm going to call this A, ray A, B. And then it's going to extend out in another direction. Let's go this way. I'm going to put a point over here that says C. So this is two rays. There's ray AB, and then there's ray BC, and together they form an angle because they have a common starting point of B. So there's a couple different ways that we can name angles. So for this one, we can name it either by its vertex, which the vertex is always like kind of where the two rays meet. It's like the corner part of an angle. So we can call it angle B. But sometimes you're going to get diagrams that have a bunch of angles like kind of connected together where they all share a vertex. So like say I had an angle that went out like this and I was looking at this angle, then that angle could technically be called angle B as well, because it shares that same vertex. So we want to know how to name angles more specifically when that's the case. And you can name them more specifically by using three different points with the vertex in the middle. So it could be angle B, or it could be, say, angle ABC. And you could, if you wanted to, technically go the opposite way. So you could call it angle CBA. It's totally up to you. And then to write the measure of an angle, we use a lowercase, kind of, lowercase, sometimes cursive, sometimes not, m, to represent angle. So let's say this measurement is 10 degrees. So I would write that as the measure of angle B, or the measure of angle ABC, is equal to 110 degrees. So it's always important that when you are writing the measure though, that you include that little n in front, because that means measurement. Okay, the next section is the protractor postulate. So starting from the top, the points along an arc can be matched in a 1-to-1 correspondence with the real numbers from 0 to 180. So kind of like halfway around the circle. The difference, remember difference means subtract, between two values along the arc is the measure of the angle with the sides that passes through the 2 points. So I know, pretty wordy, but if we were to break this down, it says the difference between the two values along the arc. So we have to take the two values along the arc and subtract them, because difference means subtraction. So we're going to do 100. Actually, I'm going to say this angle is just called angle 1. So I'm going to say the measure of angle 1, because that's all we have to like label or name it by, is just that 1 inside there, is equal to the difference between the two values. So it would be 122 degrees minus 49 degrees. So 122 minus 49 is 73. So the measure of angle 1 is equal to 73 degrees. So the protractor postulate just pretty much says that we can take an arc and kind of like, if you were to picture placing a protractor over your arc and kind of assigning it number values, we can find the angle with that protractor by finding the difference between the two values that the arc lines up with. And then last addition postulate for today, so angle addition postulate. So we've done the segment addition postulate and the arc addition postulate. And so far they've both said that, if we just add two smaller things, we get the size of the bigger thing, for lack of better terms. And this is no different. So try not to let like kind of the wording throw you off, because once you see the picture, it's not as bad. So if D is located on the interior of angle ABC, so I have angle ABC right here, and then D is inside of it, then the measure of angle ABD, so angle ABD is this one right here, plus the measure of angle DBC, which is this one right here. Those two added together, their two like individual measurements, will equal the measure of angle ABC, which is this whole thing. So if you take the two smaller angles together that are side by side and add their measurements, you will get the measurement of the full-sized angle, so the bigger angle.